Good evening, everybody. It is currently 8:13 p.m., February 22nd, 2018, which means it has been uh, four or 5 weeks since we began this experiment. Okay, so let's take a look at the crystals. It's about a month into the experiment. You can see very clearly there are a lot of crystals in the bottom of the saturated solution. Yeah, there's a lot of crystals. Some are larger, some are smaller. You can see that clearly. Okay, so there has not been too much of a change in environmental factors. The weather has been fluctuating over the past 2 weeks, but the temperature in my dorm has remained relatively same, around 70 degrees Fahrenheit. There shouldn't have been too much change in humidity either, as the crystals have remained indoors. So I haven't moved the location of crystals. So the humidity should be relatively the same. Okay, so growing crystals in warmer temperatures allows the crystals to form more slowly, which allows impurities to be expelled before they get formed within the crystals, right? So it creates larger, more prominent crystals. And a way to grow one really large crystal would be to first let the saturated solution sit for a week or so. Once you have some crystals growing, then pull out and separate the largest crystals and isolate that largest crystals into the saturated solution. So it's the only crystal that is taking the effect of the saturated solution, and it will grow larger and bigger. And is that happening right now? No, that's not happening, because there are many. You see that? Yeah, many small crystals. I see a large one there, but that's not happening here. They're all evenly distributed. Okay, so what is despacing? Okay, when a crystal is observed, you're gonna notice there are patterns of repeating crystals. You might have to look for these patterns. It may not be so obvious, but you will find patterns of repeating crystals. If you draw a plane through the repeating crystals, you're gonna get repeating parallel planes. Okay, so despacing is the distance between the spacing of these planes, and these planes are going to have consistent spacing, right? Because it's a pattern, right? The spacing is going to be consistent, and the despacing is significant because it affects the wavelength that will fit between the crystals. Okay, so the despacing is needed to compute the wavelength. So once again, the despacing is the parallel planes that is the spacing between the repeating parallel planes that are drawn in the patterns of the crystal. Okay, so how do we find despacing? Okay, so based on right here, based on this picture right here, we're gonna look at the most intense peak, which is around 20. You can see that around 20 degrees, and there. So I said the intensity was 1250. It doesn't really matter though. We don't need that in our calculation. So it's about 1250, 1250, and I said the degrees about 20.5. If you notice right there, it's about 20.5. Okay, so the formula is 2d sine theta equals n wavelength. We were told to use 1 for n, so it becomes 2d sine theta equals wavelength. Rearrange the equation to find d, so that's d equals wavelength divided by 2 sine theta. Notice that theta is given, it's called 2 theta, right? 2 dash theta, so I divided that by 2. I thought it was 20.5 degrees, so I divided by 2, so it becomes 10.5, right? 2 sine 10.5, and the wavelength is 0.15418 nanometers. Where did I get that number? Right here. 0.15418 nanometers. Alright, top right corner. Okay, and I just plugged into the calculator and got D equals 0.433 nanometers. Alright, that would be everything for today. Goodbye.